All right. Polar area is something that is absolutely covered on the AP exam. And so yesterday when we were learning about how to graph some of those fancy polars is because that's kind of a prerequisite into being able to figure out how to find the area in some of these things. Now, in many cases, they're going to provide the graph for you, or they're going to let you use your calculator. But in some cases, like in some of the problems I'm going to show you today, we do have to know how to come up with the graphs too, okay? And I'm just going to start you with the formula. And this is, you might want to have your book open if you want, page 242. This is the formula for polar area. And I'm not going to go through where this formula comes from. I'll explain it though. However, in your in Canvas, in this assignment, of course, like every assignment, there's the video of the instruction. But below that is a video where I found on Khan Academy, where he basically derives this formula. So it's only like a 6-minute long video. So if you're curious at all about where this formula comes from, take a look at that video. And he does a pretty good job. Look, I don't know how much experience you have watching Khan Academy videos, but you know, Sal Khan he's a genius, and he does a really good job of explaining stuff. So I would encourage you to look at that. All right. Let me explain what's going on here. The key thing here is it's the radius squared. And if you think about area of anything, right? When we thought about area of circles, since we're talking about polars, there was a pi r squared. But that's one of the things that sometimes kids forget to put the squared on, and it gets you kind of in trouble. And the half always is in front, and in that Khan Academy video, you'll see where that comes from. And then we're integrating with respect to theta. Now these two angles are the limits of integration. So there'll be a smaller angle and a bigger angle. And yesterday we spent a lot of time talking about angles and finding angles and that kind of thing. And so today it's going to be important. Usually what's going to happen is we're going to find the area of two shapes that intersect in some way. And you're trying to find the inside area when they overlap. And so you've got to find these points of intersection. And the points on a polar graph end up being the angles. So that's where these two angles come from. This is alpha, this is beta. I know you're not used to using a lot of Greek letters yet in your math life, but it's going to get increasing. It will increase more and more as you go through time. But this is alpha is just an angle, beta is another angle, and that's what we're going to integrate with respect to. Now, we're going to go through 3 different examples today, and one of them is kind of an intermediate thing because it's going to allow us to get to a place where we can find the area. All right, so this first one that we're going to use example 1, it's on the same page, all right? And I just already put our grid in because we're going to do that. And in reality, most of these problems, when you're finding polar area, you can't do without seeing it. You know, much like any word problem, having a picture is helpful. And having a picture, of course, of a polar graph for these is helpful as well. So in this problem, it says find the area of one petal. All right, so they're already telling us that it's a rose polar graph, which we know by looking at it, it is going to have symmetry about the x-axis. This 3 tells us how many petals there will be. Okay, and since it's odd, it's exactly that many petals, so there'll be 3 petals. If this was an even number, it would be 2 times whatever that number was, that many petals. And you can play with these kinds of things on your graphing calculator if you want to make some cool designs, just FYI. And this 3 is our maximum value that it can be, okay? And so we're going to start off getting an idea where the graph is. The thing that's nice is we know on these rose petal curves, each petal is always the same size. So we don't actually have to graph the whole thing. And in fact, we're not even going to find the area of an entire petal. We're gonna find an area of half of a petal, and then we're just going to multiply it by 2 because of the symmetry. okay? And so we want to look for those sort of easy points to find first. And the easy points to find, really, I want to find where my pedal is the longest, where it sort of ends the tip of the pedal. And since the highest possible value for cosine is 1, I want to figure out what values for theta will make cosine of 3 theta 1. And we know that the cosine is 1 at 0. But because of the 3, there's going to be 3 of them. And so we know that it's at 0, it's 1. And then at 2 pi, it's 1. And then at 4 pi, it's 1. We can't use pi because that's negative 1. So what we're trying to figure out is what angle for theta will I get to make 3 theta 0, 2 pi, and 4 pi. And of course, from here, it's just a matter of dividing by 3. And so theta is going to be 0, 2 pi over 3, and 4 pi over 3. And as you can see, I mark those. So that gives these values, when I plug in here, will make this one of these, which will make the cosine 1, which will make r 3. There's sort of a domino effect there. So notice here at 0, I have 1, 2, 3. At 2 pi over 3, the radius is 3. And at 4 pi over 3, the radius is also 3. Okay? Now, we don't have to get crazy specific about our graph, because once we start getting a feel for it, then this is not going to be that difficult. The trick is when the pedal closes, that's where these angles come from. So we're going to graph some more of this, and we're going to use some other easy values, okay? And so another easy value for the cosine is going to be pi over 2, right? When the cosine is pi over 2, then the cosine equals 0, okay? But what I really want to look at is when 3 theta equals pi over 2. And then I know that when theta is pi over 6, it's going to come back to 0. So at this angle, pi over 6, the pedal, since this is the middle of the pedal, is going to kind of get it back to 0 right here at pi over 6. All right, and so what that gives me is something that looks like this. Now, notice right here that the 0 occurs at pi over 6. Let's understand what's happening with the cosine and the radius of this particular rose petal curve as theta is changing, okay? So when theta is 0, r is 3 because the cosine is 1. Okay, so that's the longest the pedal can be. Then what happens as we're rotating, the angle forces the radius to get smaller and smaller and smaller and smaller and smaller as I rotate until I get to pi over 6, and then it's back to 0 because pi over 6 will make this pi over 2, which makes this whole thing 0. And so if you think about it that way, I have a radius, my initial big radius, then I rotate a little and it gets a little smaller and a little smaller and a little smaller till eventually it comes back to 0, all right? And the thing that's nice is that once we know that, I know what the rest of this pedal looks like, right? Because of the symmetry. It's symmetrical about the x-axis. So I know the rest of this pedal is just going to look like the same thing but flipped. And we can draw it if we want, but the reality is because of the symmetry, if I find the area between the x-axis and this top of the pedal and then just multiply it by 2, I will have the area of the whole pedal. Okay? Are you with me on that? Okay, good. All right, so let's put that into action a little bit. And like I said, you'll want to have your calculator out because most of the integration is going to be done on the calculator. Now, what's important here is when we set up our integral, we started at theta as 0 right here, and as we rotated, we ended at pi over 6. So when we set up our integral, those are going to be the limits of integration. This is going to be my alpha. This is going to be my beta. This is r, so I plug this whole thing in and square it. And so my setup looks like this. And oftentimes, and we'll get to some of that volume stuff later, they'll ask you just to set it up and not actually figure it out. But in this case, we're going to actually figure it out. So my 1/2 from the formula, my 0 for my lower limit, my alpha, my pi over 6 is my beta, because that's when it comes back to 0, and then I just take my r and I plug it in. Now, this is only the area under this curve right here and the x-axis. Okay, so this space right here. But because I have to find the area of the entire pedal, what I'm going to do is just multiply that whole thing by 2. And notice I drew the rest of the pedal in kind of crappy, but just to give you an idea. And so this is at 11 pi over 6 is where this one falls back to 0. Again, it's all that symmetry. So go ahead and punch that in your calculator. Obviously, the 2 times the 1/2 then cancels out, so you don't have to worry about that. But go ahead and put this in, and let's see what you get. Yeah, so that's a good question. So if you just did it as 3x dx, you'll get the same answer, I think. And now I think about it, I don't know, because of the limits of integration. Let's try it. Let's try both and see what happens. I know when it's in polar mode, you'll be actually able to get the theta instead of the x if it's not in polar mode. That's a good question. I don't think it matters.
I got 2.35.
I'm sorry, how many decimal places did you say?
2.356.
Does it truncate and round to the same thing? Is
Yeah.
it 6 and then it's something lower than 5?
Yeah.
Okay. You agree with Jackson? Yeah, good. Okay. Were you in polar mode or were you in normal mode, function mode? Okay. So yeah, I guess it doesn't matter. I don't think it would. Andrew, you good?
Yeah.
Okay. Now, I went through a lot of stuff here, but all of this is necessary in order to come up with these 2 limits of integration. All right, so that's why we did what we did yesterday in 10.2 in order to figure this part out, okay? All right, let's move on to the next example. And the next example is setting us up to find the area between 2 curves or outside of 2 curves, that kind of thing. So this next example wants the points of intersection of the graphs of a lemon zone. And what kind of shape is this? R equals 1.
Circle.
Circle, very good. Okay, it's just telling us we've got a circle where the radius is 1, so the diameter is 2. Okay. Now, there's 2 things about this problem that I want you to be aware of. One, the graph is important for this problem. However, it's not always important for problems like this. And I'm going to show you both pieces. And this is where being able to quickly graph and or quickly look at your graph on your calculator will become helpful as a point of check. Because in reality, we should be able to set these 2 things equal to each other, and that should give us the points of intersection, right? Just like Algebra 2 days when you found the solution by graphing, right? The point of intersection was the solution. We ended up setting them equal to each other in substitution in order to come up with our x's and y's. The problem for this problem is it doesn't always, for problems like these, it doesn't always come out. And I'll show you what I mean here in a second. All right, so we know this is a circle, radius 1, easy peasy. Okay, that's my circle in red, radius 1, boom. All right, now we got to go through this, and I'm going to go through this a little quicker than I did yesterday because I'm assuming that you've had some practice at it. This is a lemon zone, and I want to find the nice values of theta for cosine of theta that will give me some good values for r. So I'm going to start with 0 again for theta, and since cosine of 0 is 1, I have 1 minus 2. So r is -1 when cosine is 0, okay, for this limit zone. That's the first easy one that we can come up with, and then I went ahead and graphed it. Okay, -1, 0. So normally, right, this would be 1, 0, but because r is negative, it flips over to the other side. Okay, and it looks like we have a point of intersection, so that's good. Now, my next easy ones are when cosine is 0. So cosine is going to be 0 at pi over 2 and 3 pi over 2, which means r is going to be 1 at those two angles. And so it looks like I have 3 points of intersection now on the graph. So that's good. Maybe there's going to be more. We don't know. We really only have one good easy value left for theta. And that's what value haven't I used for theta that we should probably use? Pi. So cosine of pi is -1, which -2 times -1 then is +2. 1 plus 2 is 3. So r is going to be 3 when cosine, or when theta. We already had the 3 points of intersection right here without doing the whole graph. As it turns out, it is certainly possible. It is certainly possible that pi. Okay. So we're starting to get an idea of the shape. All right. It's going to be, since it's has x-axis symmetry, it's going to be a limit zone on its side versus like what we were doing yesterday where it was kind of vertical. We need some more points though. And there's not really good points left. One of the things we talked about yesterday was 60 degrees or pi over 3. And so if I can get cosine to be a half, that'll make the math a little bit easier. And so the cosine of pi over 3 is a half. And so -2 times a half is -1. So 1 minus 1 is 0. So there's a nice one too. 0 pi over 3. Now, you're starting to see that maybe it's folding in on itself on the inside here. And we'll kind of see how that ends up looking, because normally they'd be spaced apart, right, to get that little... This kind of thing, and I know you asked about this yesterday, was this kind of thing making me believe that there's going to be a loop in the middle. Because normally they would sort of approach that middle point here. But because of this, that makes me think it's going to loop somewhere, and it's going to stick itself out here and maybe even touch this circle a little bit. We're kind of out of good points. Is there a way we did that? Is there a way to get a 2 out of this? -1/2. Yeah, let's look at that. So if pi over 3 is going to give me 1/2, what's going to give me -1/2? Because then this would be -2 times -1/2, so +1. I think that would be good. So we're going to look at some reference angles of that. So if I've got 2 pi over 3 and 4 pi over 3, we should get 2. Okay. So again, we're starting to see the shape of it a little bit, but this point here makes me think we're going to have a loop, which means I really want to look at something in here to see what's going on with it, or maybe even something in here, okay? And like I said, we've run out of good points, and so I'm gonna pick, and I set this up ahead of time, I'm gonna pick a point right in here at 5 pi over 12, and then 19 pi over 12, I think. And I did this ahead of time, so you can just trust me. But there you're starting to see where it's going to flip around and do a little loop-de-loop in the middle, okay? And I don't think I can with any more. And so now I'm just going to connect them. So see how that point here was the point that kind of gave it away for me, that we were going to have to loop around. Right? The thing that's nice about all of this, okay, is that there are no more points of intersection. We had found them right away here. But I want to show you something, why the graph was important. If I would have just set these two things equal to each other, which I'm going to do on the next slide, I want you to see what happens. And I just have all the work there, just so you can see it, all right? So I'm about to leave this slide. Was negative 1, 0. Okay? And
Oh, is it only like?
yeah, it don't. So what was interesting with this particular problem, again, this is unique for this problem. It's not always going to happen like this. Back end of the limit zone would go further here, right? And then we maybe could have had a couple more points. But I'm guessing the only way that you could find that is using that substitution, and you'd come up with multiple points that way. Is a tangent point, right? Right here, this point is a tangent point. It's really not a point of intersection. It's a point of tangency. So, yeah, interesting. All right, let's get on to the next one. And so right here, if I set 1 minus 2 cosine theta equal to 1, right, then I subtract the 1, then I divide by negative 2. The cosine of theta is 0 when theta is pi over 2 and 3 pi over 2. Right? Which means, and r is 1. Like, r is always 1. So when you plug pi over 2 in and 3 pi over 2 in, r is going to be 1. So it gives me 2 points of intersection. But we know from the graph that there are 3. So doing just this isn't enough. You have to also look at the graph. Now, when we look at our table and we look at our graph, okay, the very first point we came up with, our third point could be negative 1, 0, or it could be 1 pi, right? So the question is, since these two are the same points, which one is the better one to have, do you think? Is there a better one? Does it matter? I can see 2 heads shaking. Jackson, you're still thinking about it. Is one of these better?
No.
I mean, they're the same point. Here's the slight argument that I would make that this one is better. They tell us that r is 1. Okay. Now, could you put either one since they land in the same place? Sure, but I'm going to say the 1 comma pi is better. But here's the thing. You couldn't get either of these points if you didn't have the graph. Because these 2 points are the only 2 points you could get. Now, I guess you could flip them around, negative, 1, 3 pi over 2, and negative 1 pi over 2, or whatever. But, again, this is why looking at the graph is important. I think, for the most part, on the exam, if they wanted you to do this, they're going to give you the picture, or they're going to let you use your calculator. Because I know for a fact that they do not test you on your ability to graph a polar graph. They will test you on your ability to find the polar area. So I feel like they have to help you in that way a little bit, whether it be with technology or with the graph itself, okay? I don't know that for certain, but that is that seems to make the most sense to me. All right, now let's get into a harder one.
Wait,
Go ahead.
Go back to the graph. I don't know if I do wrong. Mine has let's see, it intersects at 4 times.
Oh, that's an interesting thought, okay? Because from this, unless something is squared, how are you going to come up with more than two solutions? And I think the answer is you're not. And I think it's unique that the third point is actually want a calculator for this because we're going to graph this using our calculator instead of doing it by hand. It's going to just make our life a lot easier. And this kind of problem would let you use a calculator. So these kinds of questions, when you have two different graphs, they're going to ask you things like the region common. Okay, so that's like the intersection. It could be the union sometimes of part of the graphs. It could be just the outside of the graphs. They could give you a picture of the graphs and have a shaded region that they want you to find the area of. Okay, but what we're going to do here is we're going to use what we were doing in 10.2 to graph some of that information, finding those points of intersection and really getting a visual of what we're looking for. Okay, so while you're entering that in and putting that together, I went ahead and did it already. Okay, and so you can kind of compare yours to mine. Hopefully they look the same. Zoom fit's the key, remember? After you type, one, you have to make sure you're in polar mode. Two, you're typing this into R1 or R2 or wherever, and this is a different R. I would definitely make sure that if you can, because not all of you can have different colors. If you can have different colors, that is really helpful to clearly see which one is which. Of course, this is a lemon and this is a circle. It just looks like an oval on the screen. But that's not really that important. What we're trying to find is the area of intersection. And that's what the region common means. So we're talking about, and I'll just sketch it in here. We're talking about this region. That's the area we're trying to find. Okay. We're trying to find this region. Now, in order to do that, what we have to figure out is, first off, I'm just going to tell you this. Right? The area of this part and the area of this part, because they are both symmetrical with the x-axis, the cosine tells us that, this area and this area are the same. So similarly to what we did with the first example, if I just find the area of this and multiply it by 2, I will have the area of the whole thing. Okay, so we're gonna approach that the same way. The trick is, and this is a brain teaser for you, is figuring out when am I using this formula, when am I using this formula. And what you should be able to see is that, and I'll draw this in here, is that right here, not quite right there, I'm going to slide that over a little bit. Oh, what is happening? There we go. That's better. I'll take that. Okay, so this portion of the area goes with the circle, right? But then when we move to this side, it all is connected to the lemon zone. So what we're going to do is we have to split it up. And we're going to find the area of this part using this equation. Then we're going to find the area of this part using this equation. Then we're going to multiply all that by 2, and that'll give us our final answer. Now, the issue is, and this is why we did example 2, is this is a point of intersection. So this point, this theta, this angle is going to be used in both of my areas. Okay, and then since I'm going to stop over here, that angle is going to be used. And when I start over here, this angle is going to be used. All right? So that's what we're trying to do. Now let's do it one piece at a time. Here's the first piece, okay? We're gonna find the area just of that, and I made it red because it goes with the circle, right? I mean, it's literally touching the circle. The trick is I need to know what this angle is here and what this angle is here, because that's what's gonna go in for my alpha and beta. This whole thing goes in for r n squared, okay? Questions on that so far? All right. Then after that, I'm gonna find the area under the circle. Do the same thing. I'll need this angle and this angle. I'll plug it into the formula using this one now instead of this one. And then we'll add those two areas together and then multiply the whole thing by 2. Okay? Now, we also, again, have to multiply by 2. We have to add this in as well. So let's find the point of intersection. Let's find this value right here. Okay? And we can do that by setting them equal to each other. Hopefully. We'll see what we end up getting. Okay? And so when I set these two equal, and I did all the work up here, it's going to be up here. This is what it's going to look like. So you can follow along, and I'll go through where these values came from. All right. For starters, I just set them equal. Negative 6 cosine theta equals 2 minus 2 cosine theta. Add 2 cosine theta to the other side. That gives me negative 4 cosine theta. Divide by negative 4. That gives me negative 1/2. Okay, and we just actually talked about the cosine of negative 1/2 in one of those other problems. So we're talking about over here in quadrant 2 or quadrant 3, because that's where the cosine is negative. So I could either be at 2 pi over 3, which is what this angle should be, or 4 pi over 3, which is what this angle should be. So I don't need, I don't have another point of intersection, but I do have, like here, I have this third point of intersection, which is that tangent point. But that's not in play for us right now, so it's not a big deal. So I think our theory that we were talking about before is that extra third point of intersection is only ever going to be a point of tangency. So anyway, here's why this is important. If this is 2 pi over 3, this is the end of this area. So this is the beta for this area. What I need to know is what's this angle here for the start of this curve. Now, you might be looking at this going, well, it's 0. Look, obviously it's 0. It starts at 0. Well, what we really have to ask is, when is this 0? Is this 0 when cosine of theta is 0? No, it's negative 6. So this angle cannot start at 0. When is r equal to 0? What is theta equal to when r equals 0? Pi over 2. So my pi over 2 here is how I get my r to be 0. So that's actually my starting angle. So I go from pi over 2 to 2 pi over 3. And there's 2 of them, right? There's this one and there's this one. My first setup looks like this. 2, because there's 2 of them, 1/2 from pi over 2 to 2 pi over 3 of my r squared d theta. That will give me that area there and this area here, right? Because there's 2 of them. Questions about that? Yes, sir.
So, when we're taking like normal area under a curve, like it usually goes, like in terms of the limits of integration, it usually goes like left to right.
Mm-hmm.
But for the polar, you go right to left.
Yes. Because we're going counterclockwise. Because of the rotation. Right. Right to left are usually a normal integration, we're looking at our x values, right? And so our x values increase from left to right. But because in polar graphs, they rotate positively counterclockwise, it goes from right to left. So yeah, opposite. Good observation. All right, now we know the starting. Oops, don't want to do that. We know the starting angle here. This is 2 pi over 3. Can we safely assume that this angle is pi? Well, let's test it. Let's say that this angle is pi. What should happen is we get 4, right? 1, 2, 3, 4. So if cosine of pi is -1, so -2 times -1 is +2. 2 plus 2, that's 4. So that's good. So we can conclude that this is 2 pi over 3 to pi. Now we put this in for r squared. And again, I have 2 of them because I have to have this region down here as well. Okay. So I start at 2 pi over 3, end at pi, put my radius in and square it, multiply it by 2 to get the bottom part. Okay. Now, I would not recommend necessarily doing all this in one step. Maybe you want to do this one first, plus this one, because the 2 and the 1/2 cancel, but that's up to you. I'm gonna let you try it. So go ahead and type that all in. If you want to do it by parts and by pieces, that's fine. Remember, rounding 3 decimal places. Now, that being said, if you want to find the value of this first, you can just leave that in your calculator without rounding it, and then just arrow up and hit enter plus enter, and it'll bring that entire number down. It's up to you how you want to do it, but go ahead and give that a shot. And then you can check the screen when you're done. See if you got the same thing as me. So depending on how you entered this in your calculator, you could have gotten 15.707 if you truncated. Again, I feel like they've made this exception for, I get it, the AP exam is not testing your ability to round, but like, come on. That's like a basic thing. But I feel like they just decided they didn't want to keep docking kids points because they don't know how to round, because that's not what we're testing on the test. But